Yeah.
Hey, Steph, you please confirm if you can hear us? Well,
Yes, good afternoon, guys. I can hear you well, and I just started recording.
all right. Thank you very much. Hi, everybody, and welcome to our seminar this month. We are super excited to, host Skylar, Dr. Skylar Speakman today, and he's going to speak about subpopulation identification of multimorbidity in Sub-Saharan African population. So Dr. Speakman uses machine learning and data science to impact people's lives across the continent of Africa. He is a first-line manager of the AI sciences team at IBM Research Africa in the Kenyan lab. He received a PhD from Carnegie Mellon University and was a founding member of the Event and Pattern Detection Lab. Before CMU, he earned master degrees in mathematics and statistics from the University of Kentucky. So in his talk today, Dr. Speakman will, share a new approach to identifying multimorbidity when two or more diseases occur together across large data sets from Nairobi, Kenya, and Agincourt, South Africa. His team's method automatically, detects high risk subpopulations that traditional analysis might overlook, offering fresh insights for public health research and policy. I'll let Skylar share his slides in one step. Stop sharing.
One window share. Let's see if you all can see my screen now. There it comes up. Great. Thank you for the introduction. That was a trip down memory lane. You also used a very outdated photo of me. I didn't recognize that young man in the photo. And you also reminded me that before moving to Kenya, I was a professional student and had collected lots of degrees. And actually, I'm very, very blessed that even now, 15 years later, after doing that stuff within the Event and Pattern Detection Lab, we still get to use some of those methods. So it's very, very rare for that type of longevity to happen. And I recognize that. So yeah, thanks for the intro. Yeah, that was history. Today, I'm going to talk about this paper here. It came out in Nature's Scientific Reports a few months ago. It's obviously a much, much larger effort, which I guess I'm the oldest author on this paper now, at least, or the overseeing author. If you notice, pay close attention, Gurma's name is also on this. Gurma was a part of this project when it first started many years ago. So let me start off by giving you a bit of background about why this paper exists and the entities around it. Then we're going to do a mini lecture on upset plots. Hopefully you guys have seen upset plots before. If not, you're going to learn something about upset plots. And then in the third part, we'll talk more about the methodology and what we found in this particular data set. All right, so to get started, this is actually part of a larger body of work started by the NIH, the US's National Institutes of Health. And about 5 years ago, they kicked off a $75 million grant with the aims of improving data science on the continent of Africa, specifically towards healthcare. Now, so many different facets of this large grant, everything from capacity building to what we do with policy, ethical, social, legal concerns, how do we share data, all of those things are trying to be encompassed within this larger program. So that's kind of the umbrella part of the paper. And then within DSI Africa, there's a research hub called MADIVA. MADIVA stands for Multi-morbidity, Digital Innovation, Visualization, and Applications Research Hub. Right? So this is a hub being funded by the larger NIH with that goal of increasing data science use on the continent. Now, within MADIVA, you guys can see the hierarchy here. There's lots of other partner programs, of which IBM Research is one of them. So that's how I kind of come into this larger picture here. NIH the DSI program. Within the DSI program, there's Mediva, and that's where we're talking more about multi-morbidity. But then even with Mediva, lots of different partners coming in here. Some directly on the healthcare side, APHRC, some of you may be on the call. And then IBM Research is bringing some of the methods space to it. All right, so that's kind of the landscape about what's sitting behind these papers. They don't just emerge out of nowhere. It really takes lots of great organization skills ran out of Mediva. All right, so now let me bring to kind of the first point of the paper, the one we'll probably spend the least amount of time here, but I don't want to downplay it. Multimorbidity, in our case, these are the chronic diseases. Think your hypertension, your diabetes, your heart disease. These are becoming increasingly more common in sub-Saharan populations. So it is here. It's bad. It's correlated with premature mortality, increased use of healthcare facilities, if you're just thinking about how much money you cost to live, and much lower all quality of life. So although other diseases, the ones that spread more virally, not the chronic cares, might get more attention overall, this really is a much larger concern and growing on the continent. We also think care of it is fragmented, leading to lots of dropped balls and more complicated treatment patterns. So Mediva's overall larger goal is what can we do with existing data sets to help communicate these patterns that we're finding here. Don't take my word for it necessarily. All of these points are broken down in a paper that also came out earlier this year, the Mediva protocol paper. So there's I can find these links later. You can check this one out. This really goes through in much more detail than emojis allow on what's going on with multimorbidity in sub-Saharan Africa. All right, so point number one, multimorbidity is incredibly important. You probably know people with a lot of those chronic conditions now. So please take care of yourself. But we're not going to talk too much more about the actual healthcare side of multimorbidity within the rest of this talk. So we can talk more about some of the data and methods. And in fact, Lee will help introduce this one. One of the facets of DSI Africa, all those multiple facets one, was what can we do for new data collection techniques and systems? That's where this work falls in that space. So great other work going on in capacity building, the social legal implications, but this part of work really is on new ways of looking at data or finding patterns in data, which is one of the goals of larger DSI effort. Okay, so now we're going to transition a little bit into item number 2 on the list, and this is the upset plots. This is going to be me doing a little bit of a detour on a small lecture. A quick show of hands. Are people familiar with upset plots? All right, 1 out of here. Great. So, okay, that makes me very upset now. Upset plots are about 10 years old, and you can think of them as more structured forms of Venn diagrams. So if you have ever tried to make a Venn diagram that has 4 different circles or so, the intersections get out of control, and it's ugly and it's hard to read. So the takeaway from this, in addition to multimorbidity really is a large concern, the second takeaway is please consider upset plots if you ever have to use a large Venn diagram. Right? So I've got a few takeaways here about how we can read an upset plot. This data is collected as part of the Awagen project, a 5-year-old, probably actually 10-year-old project, and they take health surveys between people between the ages of 40 and 60. They do this in multiple parts of sub-Saharan Africa. We're looking specifically at the Nairobi data set today. So a total of about 777 respondents. In the lower left-hand corner, we have our 4 different diseases that we're looking at: diabetes, chronic kidney disease, cardiovascular disease, and hypertension. A small little note here. For those of you who are writing papers or reviewing papers, please look for spelling errors on graphics, not just spelling errors in text, because this slipped by every reviewer, it slipped by every author, and there are spelling errors in the graphic. All right. These bars associated with each of these conditions here can be thought of as the size of the Venn diagram circle that you would like to draw. There are 500 or so respondents in Nairobi of the 1,700 that have hypertension. there's 250 or so of the respondents that had kidney disease. Right, so these bars off to the left are telling you the relative sizes of those 4 different conditions. Hypertension being the most common, cardiovascular disease being the least common, at least in this particular data set. So that's what those rows mean. Now for the columns. This column here is specifying if you have hypertension and only have hypertension, you're in this group here. So there's 355 people that have hypertension and only hypertension. If you were thinking about this as a Venn diagram, this is one of the leaves on the side where there's no other intersections. The rest of all these different columns represent all the other possible intersections that may occur. So for example, you can look at this, what I call the stitch or the code for hypertension and kidney disease. There are 81 individuals that fall in that intersection. And then you can piece this out the rest of the way. So again, think about a 4-circle Venn diagram that looks a little bit weird about where all the numbers fall. This is an alternative to Venn diagrams. And I do think takeaway number 2 from this, consider upset plots if you ever have to write a much more complicated Venn diagram. Okay, why I took this long little detour here is because this helps really emphasize how, for this paper, we defined multimorbidity. If you have 2 or more of these chronic conditions, we are considering you multimorbid. It's not a great definition, but it is a start. And we do spend a bit more time in the paper talking about everyone's kind of got a slightly different definition of multimorbidity. But for the purposes of this analysis, we're talking about people that have 2 or more of these chronic diseases. And that comes out to about 10% of the respondents from the Nairobi data set. All right, so the upset plots wasn't entirely out of the line of thinking here. We do this to emphasize 2 or more diseases is now our outcome of interest. And we do group people that have hypertension and kidney disease the same way we would group people that have diabetes and cardiovascular disease. So our requirement is just 2 or more. Okay. All right, so upset plots, very cool. Check them out. Really used more often in the healthcare space. Now we'll get to the third part of the presentation. Multimorbidity is here. It is a larger concern. One way to represent this is to consider people that have 2 or more diseases, and upset plots help us get there. But now we've got this statement that in Nairobi, approximately 10% of the respondents to this study did qualify for our definition of multimorbidity. So that statement's pretty clear. We can defend that. A follow-up question now is, who are these people? How is multimorbidity distributed through the populations? Does it vary by age? Does it vary by sex? Does it vary by BMI, by blood pressure, by triglycerides? So many different questions now beyond just the statement of the mean 10% of individuals have multimorbidity. So now we're going to call this this larger effort stratifying the outcome. You know what you want to see? You've got expectation about 10%, but how does that look like across different groups? One way, and probably the most common way, and this goes back hundreds of years, there's examples about people that break down an outcome by different categories going back hundreds of years ago, is by sex. How does multimorbidity rates vary between males and females? And in this case, we can make the statement that females are about 1.6 times more likely to have the outcome of interest. So not terribly interesting, but it's emphasizing that this sort of question is asked all the time about how outcomes are distributed across populations. You can take another feature from your data set, in this case, age, stratify the outcome of interest across a different feature. And this one, actually 55 and older are 3 times more likely to have multimorbidity. Interesting tidbit. Can we go a bit farther? Can we do 2 features at a time? So now we combine some of these together and we talk about older females. And now the odds ratio specifically increases even farther. The point I'm making for all this is not for you to remember these numbers in your mind, but the fact that these are really commonly asked questions about an outcome of interest. Stratifying, whether you call it that or not, you have likely done in some sort of data analysis. And you're probably using some sort of prior domain knowledge about what features you choose to break down the outcome of interest. Right? So we want to emphasize this is done all the time in analysis, and people will typically look at the literature about how they want to analyze these things. But the reality is there are just so many possible subsets to consider. We are not going to claim that manual exploration of the data, the trial and error approaches, is wrong, but we would ask people to recognize that they aren't even scratching the surface on the number of possible subsets to consider. Is it connected to BMI? Is it connected to waist-to-hip ratio? It's connected to your blood sugar levels, your triglycerides, your diets, all of those other questions we have information on. We can't actually possibly start looking at all of the possible subsets to consider. So this is one of the actual concerns that's a problem with doing it manually. Right? The approach that we used in this paper actually removes that limitation and brings a little bit of computational scalability and discipline to the search for anomalous subsets. Doing it manually is not bad. Domain experience is not bad, as long as you recognize you aren't really doing a full search of the space. Our approaches here help you come alongside, answer the same questions you were originally, but on a much larger scale, while we do actually consider the exponentially many combinations. I do want to emphasize here, I can get a bit distracted. This was work that I had been doing for a long time, and I enjoy the methodology here, but I would bore some of my audience members here. But this space is still a large, active, ongoing area of research. We've got members from the original pattern detection lab listed here. Other ones, Mallory at Stanford, Seth is at Oxford, and they're doing lots of great work in this space. So a shout out to people that have been working on the methods that we used here. We used a more simplified method in it. All right, so yeah, don't let me get distracted and talking too much about the methodology. So what did we find? We talked earlier about what happens if you break it down by age or if you break it down by gender, and you can see these varying rates of odds ratios. Well, we've passed into our code the outcome of interest, which is multimorbidity, its expectation, which is about 10% of the population of the data set should have this, and we allowed it to do its efficient search over all these possible combinations. And here's a group that came back. Waist-to-hip ratio greater than 0.94. I don't know if everyone is now sort of, awkwardly trying to figure out what the waist-to-hip ratio might be. Triglycerides greater than 1 millimole per liter, and carotid intima media. I am not a medic, but this is a measure of plaque, which can be picked up just by a really quick ultrasound within your neck. I described these features to my wife, who is a physician, and she says, yeah, this is not a healthy person. These things do make sense. But she would not be able to write them down this way. This group of people are nearly 6 times as likely to have multimorbidity as the people outside of it. Incredibly strong signal. By the way, those numbers in red are an odds ratio, which means we calculate the odds of having multimorbidity if you're in the group. We calculate the odds of having multimorbidity if you're outside the group, and then we take the ratio. So that's how we get to that 5 times more likely. Incredibly strong signal here. This was not known by the health experts working on this data set, right? But it is, again, the odds ratio is quite hard. They doubt it would have been found through manual exploration. Doesn't condition on gender, doesn't condition on age, but it is this other group here. All right, we're going to spend a bit more time talking about the pros and cons of these two different approaches. So, one question that came up during the writing process, did we just call older females by a different name? Is this the same group, but just described slightly differently? So now I'm going to go against my own advice a little bit and use a Venn diagram, because there's only 2 cases. So a Venn diagram still, if there's only 2 cases, you can still use a traditional Venn diagram, and you don't need to go to upset plots. But the answer to this is we do believe these are 2, not entirely disjoint, but 2 separate events going on here. They overlap a little bit. If you want to calculate the Jacquard distance, it's about 0.1 of the overlap. So the people that fall into this category on the left with the waist-hip ratio, the triglycerides, and the CIMT, those are a different group than the older females that were found by a manual process. So that had come up in one of the questions of the review. So I'm going to pause a little bit on this slide, maybe even take a drink. To talk about pros and cons of when you might want to do manual exploration, where you're doing it by hand. First, this is talking about the group on the right. You presuppose the group. Before you really see the data, this is what we call hypothesis-driven approach to it. Because you've done recent literature reviews, you say, I really wonder how my outcome is broken down by sex. That's the question you have first. Then you can go do a very simple Python code, check at the different mortality rates, and then come to that conclusion. You can do it again for age. Maybe if you fancy, you can do it for combinations of them, right? But you really should limit that hypothesis-driven approach to only a few of those cases. You shouldn't just be doing them wildly. An alternative to that is on the left, where we're saying, actually, let some software go and do this search for you. Let that code process the exponentially many subsets to consider and return the subset that is the most anomalous. We did not ask for it to be broken down by triglycerides, by waist-hip ratio, or by CIMT. Those features were in the search space. Those features were in search space, but we certainly did not pre-specify a subset that uses those three. We had about, I don't want to say a dozen, 2 dozen or so features in this space to choose from. So you are rolling the dice in the sense that when you run this algorithm through it, you really aren't sure what's going to come back. And while medics will be saying that this is a sick person, they would not necessarily have sat down and written out a subset this way, which is a kind of a cool addition of bringing the data science methods into play here. Coming back to the subset on the left, this is not hypothesis-driven work. This is now discovery-driven work. You provide the expectation that about 1 in 10 individuals in your data set have the outcome of interest. You provide the features, and then you say, find me the subset where these odds ratios are extremely high. And then you're sort of stuck with, you're left with what you get. And in this case, we aren't quite sure of the entire answer. We don't know the medical connections between the multimorbidity outcome and the waist-hip ratio, the triglycerides, and CIMT. Whether or not that means that the work is worthless, I don't think it is, but it really goes back and forth between the tension between hypothesis-driven investigation of data and discovery-driven or exploration-driven. And so here in this particular paper, we talk about those different two approaches on these subsets, that example, which we showed earlier were kind of distinct from each other. We're coming up here towards the end a bit more, because I do want to have lots of questions about where the work is going now, about Medeva, other aspects of IBM. But the code for this is available on GitHub. It's part of the Trusted AI or the AI Fairness 360 toolkit. This was a bunch of methods that IBM put together and coded them up in kind of an sklearn style syntax. And so the method that we used here is available in this really useful repo. I do want to spend maybe just a bit of time. You can see here what this thing is called is the multi-dimensional subset scan, also underscore bias scan. And you're saying bias, Skylar, you've not mentioned bias once in this entire presentation. Why are you calling software biased scan? Another interpretation of this, and now I'm going to do maybe a bit more on the ML side of things, is we have a classifier in this work. We didn't call it a classifier, and it's not a very good classifier. Our classifier is everyone has a 10% probability of having multimorbidity. Right? It's extremely underfitting the data, but it's not incorrect. It's true. Everyone has a 10%. But what that statement is making is every male, 10% chance of multimorbidity. Every person over 70, 10% chance of multimorbidity. Every person with a waist-hip ratio, 10% chance of multimorbidity. Another interpretation of what we've been doing here with stratification is we're answering the question, where is that classifier the most wrong? Where is it giving the worst information? It turns out the subset where that classifier was really wrong is that triglycerides, waist-hip ratio, and CIMT group. Right? So you can think about this, if you prefer the machine learning way, is you have a classifier and you want to see where that is making the most mistakes. That's what's also going on here behind the scenes. So that's why this is what we call a bias scan code, but we've simplified the terminology a lot working with the public health research. And again, trying to leave as many time for questions, so I might even call people out online in particular, so get ready. This is, if you ever heard the expression, that meeting could have been an email. All right, well, if this meeting was an email, this would kind of be the one large takeaway for it. This was a poster one of our colleagues put together for another session. So I'm going to just, again, kind of review what we spoke about here. Multimorbidity is not one of the sexy diseases on the continent, unfortunately, but it really is becoming increasingly a concern for public health individuals. This is because Africans are living longer than they have before, and our lifestyles have changed drastically, importing lifestyles from the West. Care is quite fragmented on these sorts of things, and we don't really know the overall impact of these diseases. One way to kind of combat this is to review existing public health surveys that have been done over the years, and now start asking questions not about individual diseases, but at least cases where they overlap. We did that. We gave an example of an upset plot. So now hopefully everyone on the call understands what I mean by an upset plot. And we use that as an example of how we can classify multimorbidity, at least for the purposes of this paper, as two or more of these conditions in the same person. Diabetes, hypertension, cardiovascular disease, or chronic kidney diseases. You can imagine doing this further and looking specifically at two pairs, but we just kind of aggregated them all together. Once you have your outcome of interest, it's pretty easy to make a statement that 10% of the population, at least of the ones that were in this survey, have multimorbidity. But the interesting questions start to follow up afterwards. It's not enough just to state the mean. You want to try to understand that outcome of interest at different subpopulations, because that's how you can start really finding the insights. The problem with trying to look at data at the subset level or the subpopulation is there's just so many of them to consider. Domain expertise will get you somewhere, which is what we've done here with breaking down the outcome of interest by age or by gender. And they give you some nice insights. It really is interesting about this increasing odds ratio if you break it down by the usual suspects, if you will. We are not trying to knock or belittle people that will be doing stratification in a manual way. They know what they're doing in terms of why they're asking those specific hypotheses. Rather, we want to come around and recommend automatic stratification as something that comes alongside it. Recognize that you are not going to be able to actually do every possible subpopulation, especially as soon as your feature space gets to be about 20 or 30 features, then you're getting up in the tens of millions of possible subsets to consider. So that's where kind of data science comes in and says we can speed that process up. We can bring in some nice guarantees about what you'll find. We do this by maximizing a likelihood ratio statistic. I blurred over those parts of the plots. You guys are welcome for that. And then we applied that methodology to this particular data set with multimorbidity as the outcome of interest. Found a new subset of it. We found a new subset. They are describing an unhealthy population if you're not a medic with the combinations of those wasted ratios, triglycerides, and CIMT. And they are incredibly likely, or more likely than not having it, for multimorbidity. This group was not known ahead of time in the data, it would have been difficult to find by a manual process. Also, this group is, we think, quite distinct from the group that was found from a manual process, as you can see by the overlap between those two being about 10%, if you know what an Agincourt overlap coefficient is. So it is a unique group that we were able to kind of write down and say, look out for these people in the future. Something I also didn't cover in these slides is we took the group that was identified in Nairobi, and then we went to South Africa, that data collection site. And we said, if we use that same group that we defined in Nairobi, and we'll go over and transfer it to South Africa, does the South African population, as defined by these thresholds, also have higher rates of multi-morbidity? And yes, they did. So they do transfer across units. And we took the group that was found to be anomalous in South Africa and applied that definition of the subset to the Nairobi one. And yes, they passed also being elevated. So they were different subsets, but when you apply them to the other location, you also see elevated rates of multi-morbidity. The code that was used to run this has actually been used in the past to investigate predictive classifiers. And if that sounds completely like nothing what I've talked about, it is actually there. Our predictive classifier is simply that mean, the fact that 9.7% of the participants in Nairobi, that is us making a classifier, not a very good one, but it is a classifier where we take every individual and we give them a predicted probability of having multi-morbidity. That we know that that method is underfitting, and you can think of automatic stratification as finding out where that very naive statement that everyone has the same probability, what subpopulation is that the most wrong? What subpopulation is your naive classifier the most biased? That's what we were able to do here and how we were able to find that. So I think I've gone through actually great on time, and I do prefer that rather so we can have more people ask questions. And yeah, I think I'm right at about 40 minutes. So again, lots of great work with co-authors spanning multiple institutions, not just IBM research. These co-authors all sit within the MADIVA working group, which is a part of the larger DSI effort funded by the NIH. So it's a really great example of data science being promoted and funded here on the continent. And IBM's very grateful to be part of these of this research hub. We've also participated in another research hub called HEAT, and that one they're specifically looking at climate, more specific temperature, and the impact on maternal newborn child health. No updates on that outcome of that project today, but this is just a good, nice outcome of Nature scientific reports of what is going on here on the continent, specifically with the overlap of methodology, data science, and public health on the multi-morbidity front. So with that, I think I'll open it up to questions.
So much, Skylar, for quite an insightful talk and great work I find co-authors, Jamal, and everyone in the paper. Yeah, we have a few questions. These two questions from Felix on the chat, but I wonder if we have questions here.
Yeah, we can wait on Felix questions.
Yeah, should we just let me read one of the question and then you can. Yeah, I wonder if Felix actually you want to come on mic and then just ask the question. Yeah.
Sure. Hi, Skylar.
Hi, Felix.
Yeah, well, it sucks to be. I still get to be the first one to ask you questions.
Yes.
So back to IBM time. So the first question I had was a comparison of the upset plots between like the ones in Nairobi versus those that are in like a Western country, just for context, to put the whole problem in context, because I was curious, like, okay, 1 out of 10 in Nairobi now has comorbidities. Like, is that growing? By what rate? Like, what's the similar number in the US?
I do not know the similar number in the US. That's a really good question. The data set that we used to collect this set of results did have a second phase. So what we should do is go back to the second phase of this test and then run that same information again on the 5 years later follow-up. So we can answer that question, but we didn't. My guess is we didn't answer it for multi-morbidity purposes. They have done this for individual diseases, and the one that had the largest increase, so again, this is now kind of individual diseases, not our multi-morbidity definition of 2 or more, diabetes had the largest jump. Hypertension did continue to be the largest overall prevalence. That probably doesn't come as a surprise, but there's another paper, I don't have it linked here, from the other people within Medeva, and they looked at those 2 different time steps, the 2 different data collection parts on a per disease basis, and diabetes has gone up the highest. We actually, that is why we are working on another paper where we do have a predictive model attempting to predict the 5-year onset of diabetes, because we have enough people without diabetes at time step 1 and more people with diabetes at time step 2. And so that gives us a label to look at. We're using XGBoost. The AUC is not great, but yeah, sorry, that's a bit more of a different question. But I don't know what the answer is for the US, and we didn't actually look at the combination of 2 or more outcomes at time step 2.
Cool. So the second question was more to do with the technique itself. So is it possible to prefer certain features of others? So for example, age, sex, those are easier to put together, like for even just someone as a physician, versus those that require certain tests.
Yeah.
So that you can go ahead.
Yes. So if you're a Bayesian, another way of looking at our scan statistics, the function that we are trying to maximize, you can think of as putting a prior on this. So what that means is if the feature that you want to be there is present in the resulting subset, the score gets boosted up. If the feature that you wanted to be there is not there, the score of the subset gets boosted down. And it sounds a bit arbitrary by how much you push up and how much you push down, but you can come up with the correct numbers based off of the Bayesian prior to the binomial. So yes, you can do that. We didn't do that on this work. So every one of the features is equally likely to be a part of the most anomalous subset. In other words, we have a flat prior on which features participate. Now, the longer answer to this is we do vary the number of features that participate in the most anomalous subset. So we don't specify which ones, but we can pull a lever and say, find me a subset where there's only one feature participating in the most anomalous subset. Sorry, find me a subset of the features where it's just one, so just age. And then you pull the lever a little bit more and say, okay, I'm okay having 2 logical statements in my subset. That can be an and or an or. Or you can pull the lever back a bit more and allow it to be 3. We were able to find subsets that have 15 or 16 logical statements in their description. But just because you can find a subset that complex does not mean you want to. Interpretability goes out the window. You have to fill up half a page just describing that subset. So we do have a lever, but it's preferencing the number of features participating in the subset, not which features. And again, a lot more details in this work about what that penalty is.
Why would you preference like an and versus an or in that example?
We do not, yes. So we do the same penalty on an and or an or. I'm not actually sure if we could differentiate and say we would prefer ors or if we would prefer ands. They do get the same penalty right now because we count that as the number of logical statements that are used to describe the subset. So I haven't really thought too much if we would prefer subsets defined by ors or with ands. But on this work, they do get all equally likely. And we have, for example, here, we didn't write it out, but there are 3 ands here, or 2 ands rather. Waist tip ratio greater than 0.94 and triglycerides greater than 0. And CIMT greater than 0.64. So yeah, good call out on that one. There are implied ands in this sequence.
Cool. Thanks for this. Good to see you again as well.
Yeah.
Hope you've learned some Swahili at least.
I'm embarrassed. Yeah. You need to come teach me. All right.
Thank you.
Questions?
I had a kind of follow-up question to what Felix had. Thanks for the talk as well. Do you think that some of the common features that are used for manual exploration came out of automatic stratification at some point in healthcare in general? And in this multi-morbidity identification of these 3 that are discovered, what does that mean for healthcare professionals today? Do you think they will now use them more commonly as a hypothesis? Then they will become part of what like age and sex is as well.
Your second comment sounds a lot like you were reviewer number 2 in this process when you were trying to get it published. Yeah, so I'll try to address that second question. You might have to remind me what the first one is, but we did kind of go back and forth on, does a clinician use this? Does this influence their work? And I think we probably more landed on, we are still trying to do the messaging, I would say, more at the public health official rather than someone sitting across the patient level. So we aren't quite saying for this information to go all the way down to immediate care. Part of the work we're doing, if we're training a predictive classifier, maybe, because then someone's sitting across from you and you can see that your predicted probability of the outcome is much higher. That might make a bit more sense in the clinical setting. Here, think about this much more at the subset level, the subpopulation. So broader scope intervention in individual clinicians. Another point of view is some people, let's just take these 2 guys as an example here. They might be really quite happy with their manual find here. You can do your statistical significance tests. Yes, this is a group that stands out as higher interest. And they would say, yep, 4.91. This is our group we need to focus on. What then they might want to use automatic stratification for is, if there's a cluster here, is there some other cluster? So they still like the 4.91 older female cluster. But then they're not going to be completely blind as to other clusters. And that's where automatic stratification come in and say, even though this might not have it as an obvious medical connection to that subset, there is a cluster here. And they would not have known that if they didn't do this extra step, even though they still are very happy with their hypothesis-driven approach that they suspected sex, they suspected age, and they found it in the data set. They hopefully understand that it's not just one cluster within that data set. Are there others? Automatic stratification might be helping that one.
Yeah.
But again, think of it more probably at the public health-ish level, because we really are interested about subsets of the population rather than individuals.
Makes sense.
Yeah. And your first question, or maybe we'll,
Yeah, it was just about whether you think the features that are more commonly used for the hypothesis level probably came out of like automatic stratification or like more discovery.
I would love to make that claim. I don't think it did. They've been studying, sort of these diseases longer than probably automatic stratification has been around.
Yeah.
We did work on a paper, code, a Python notebook, kind of paper, where we used the ideas of automatic stratification similar to a lasso feature selection process. So now that you've done this, before you've done any predictive modeling, you've got these 3 extra features here that at least in combination together, because remember there's ands here, has got this strong signal. Now take this information, and go build a logistic regression model where this is your one coefficient from it. Are you part of this group or not? And we were, again, going back and forth between discovery and then using that for a predictive model. Yeah, it's still at the Python notebook stage.
I know people are working across different domain and then data sets, but I don't want this opportunity to be focused on healthcare only, because the approach could be actually applied across different domains.
Yeah.
One is to even evaluate, understand data. Whatever data you are working on, you have ground truth, just analyzing that data, the representation across different segments of the population first gives you an understanding what this data is about. Second, we even did like, okay, you provide data to any deep learning framework to, to get something at the end of it, but how different segments of the data are represented in the hidden layers of your deep learning? Could you really look at them separately? Finally, even the same approach could be used to understand your outcome and your error, right? You have data modeling your outcome. For which kind of data are you predicting differently, more erratic, less erratic? That will give you that analysis. So we even applied it into molecular domains, if you recall.
That just came out actually in Nature as well this week.
Yeah. So the idea is like you have different generative models, right? They are supposed to give you new molecules and all that. But which generative models usually sort of generate what kind of molecular representation? So this gives you a comparative understanding of maybe this model is very biased towards generating this kind of very acidic or, sort of molecules, where the other model is to the other. So I mentioned that so that you can ask him how you can, use this approach across different, because you do a lot of evaluation of models, language models, and different data sources. Yeah.
Yes. No, great knowledge. Are you on that molecule paper?
I did the first one actually a few years ago.
Right, we're on a Nature run, right?
Oh, well done.
Yeah.
Well done.
Now, Girma is also quite familiar with some of this work, and we have applied it in lots of different areas. This is a good example of applying it on tabular data sets, but we've also applied it to the representation space of foundation models, spanning images. We did it for adversarial attacks. So you can take two images and say, wow, this one's weird because it's been adversarially affected. We did that with time series as well, with Victor on audio sequences. On language models, we've done it to detect toxicity, stereotypes, and hallucinations. More recently, we applied it to personas. So this is where you sit down and you tell a chatbot, you are a helpful assistant. And we've identified where that type of persona instruction is found in these deep model representations. I think the broader takeaway from this is our team, myself in particular, really view a lot of these questions as anomalous pattern detection driven. So what's sitting underneath all these types of views is, here's a data set, here's what we expect to see, here's what we actually observe. Can we quantify how weird that is? And that's what the methodology is doing. And we've used it well beyond healthcare into large language models more recently. This particular paper, tabular data sets, really cool with colleagues working in the multi-morbidity space. But the method underneath is based on anomalous pattern detection, which is, more than a hobby. I suppose it's what I get paid to do.
Mm-hmm.
Yes, I actually did. You mentioned kind of the lasso subset selection. It'd be kind of interesting to see kind of the middle ground between the kind of domain knowledge driven covariate selection and like the automatic subset selection. Like, where does like a naive lasso, like what covariates does that pick up? And I was wondering, kind of related to that, like, is there anything in like the optimization that prevents you from picking up a subpopulation of one? So if there's like a tail population on like the high end of the triglycerides, and like it's you pick a cutoff that only has that one person on all these things, that's a odds ratio I guess like 100 to, it's like a 10-to-1 odds ratio, right? So that seems like it would, if you're just optimizing the odds ratio, you might pick up something like that. Is there further regularization to prevent like overly small subpopulations?
The regularization we've done so far has mainly focused on the number of participating features, not the size of the subset.
Got it.
But you can also penalize or reward through the Bayesian interpretation the size of the subset. So you could push that lever and say, every time you add a new row to this subset, my score decreases a little bit.
Right.
Or the other one and make it larger. So we didn't do that on this work to whether encourage larger ones or encourage smaller ones. We did penalize the number of features in the space.
Right.
A bit more interesting approach to this is what we've done in the past. We haven't directly penalized the size, but we have taken another subset, for example, older women, and we've said, find us a subset, but every time you include a record from the one we know already, decrease your score. So we are encouraging it to find diverse subsets. And that was work done by John Wamburu, who's now at Google here. So the penalty wasn't necessarily on the overall size of the subset, but the penalty was on don't look like something we already know. On the results here, we did not put that into place. We did not penalize our new subset if it contained females over the age of 55. We found it directly, and they happened to be more or less disjoint. But if you really wanted to say, find me something new, there is a way to penalize the search process so that you are discouraged from finding women over the age of 55.
The ranking also helped, right? When you identify different groups and you rank based on like the number of features and the number of sample size they have. So that will give you also the opportunity to say, this is like second ranked, but it may have different sample size compared to the first one. So that gives you that analysis.
No, lots of papers have used this sort of space. One fun one was data set in the US, cars that have been pulled over by the police, and then which ones get searched by the police. And they have breakdowns of the driver demographics, car demographics, time of day. And what we found was unfortunately incredibly predictable about the subsets that got searched. But what we emphasized in that breakdown was we did not presuppose that group. We asked the question, here are all the feature spaces, who gets pulled over the most often? And it was African American and Hispanics under the age of 25, like males. Like it's just the group. And what we really wanted to emphasize on that one was that wasn't us. We didn't start off with a chip on our shoulder saying, "Oh, I'm gonna show that the police are biased in this case." So it really was from a much more kind of hands-off of this is what is in the data if you allow the discovery-driven approach to find. So yeah, that was also one group.
Don't have any
Yeah.
charts. Right. Oh my gosh. Thanks so much, Skylar, once again for being our guest speaker and for quite an informative and insightful talk. We truly appreciate it. Yeah, thanks so much. And everybody, thanks for joining. And yeah, we'll send you an invitation for our next seminar. Bye.
Thank you so much.